This video lab report covers Lab 3, where we analyzed a macroscopic view of DC and RC circuits. The purpose of this lab is to apply the principles of charge conservation and energy conservation to predict and experimentally verify the behavior of DC series circuits and RC circuits, including steady-state currents, potential differences, and the time-dependent voltage decay of a capacitor. A preview of the main results. So we're going to refer to the measured currents as I1 and I2, and they were both experimentally determined to be 16.7 milliamps, which confirms charge conservation in a series circuit. When you reverse the ammeter, it changes only the sign of the current. This verifies correct current direction conventions. The measured potential differences across the resistors and batteries summed to be 0.015 volts, which the theoretical value was 0 volts, so this does confirm energy conservation. In the RC circuit, the light bulbs initially lit brightly and then dimmed over time. This demonstrates the exponential decrease in current as the capacitor charged and discharged. The capacitor charged in approximately 10.73 seconds and discharged in approximately 14.0 seconds, which shows the time-dependent behavior consistent with the RC time constant model. So the first physics principle I want to discuss is charge conservation. In a steady state, we're assuming that charge cannot accumulate. Current, we also know, is equal to the change in charge over the change in time. This means in steady state, charge conservation is approximately current conservation. So the current that flows into a node should be equal to the current that flows out of a node. The next physics topic I want to discuss is Kirchhoff's voltage law. This states that the sum of all voltage drops around a closed loop is equal to 0, and this shows energy conservation in a closed loop. I now want to discuss Ohm's law. Ohm's law states that the current through a conductor is proportional to the voltage across it and inversely proportional to resistance. You'll also notice in the graphs below, when resistance is constant, we have a constant slope. However, when resistance is not constant, when you compare current versus voltage, we are getting a leveling off. In the example for RC circuit physics shown to the side, an RC circuit includes a resistor and a capacitor. The energy conservation equation for that circuit is going to be the change in voltage of the capacitor plus the change in voltage of the resistor, and we're going to assume that the electrical field in the connecting wires is negligible. In our experiment, the system included the batteries, 47 ohms and 100 ohm resistors, capacitor, light bulbs, and meters. The surroundings was just everything else. Assumptions that we had to make were we assume that the wires have negligible resistance, batteries provide constant charge, resistors are ohmic, no charge buildup in steady state, and the capacitor behaves ideally. Our first experiment was a series circuit. So the initial conditions for this was we had batteries connected, current begins flowing, and we're quickly reaching steady state. As you can see by the arrows shown, this shows charge conservation. At two different locations, the current was approximately equal, about 15.6, 15.7 milliamps. In the RC circuit experiment, our initial states of our experiment was the capacitor was initially uncharged during the charging phase, and then we removed the battery for the discharging phase, and we measured time using a stopwatch on an iPhone. So for the series circuit, our results were because it was a closed loop, we were able to find the total voltage to be 0. But when we did the experimental results of testing the different components, the different resistance components, the different components of change in voltage around the circuit, we were able to come to the conclusion that the closed loop was approximately 0. Our actual experimental values was 0.015 volts, which does confirm energy conservation within some experimental uncertainty, which we can attribute to digital multimeters having small rounding uncertainty, real batteries not being ideal voltage sources, the LEDs and wire connections not being perfect conductors, and our ammeters we did assume to have 0 resistance, but in reality they do have some small internal resistance. So for our RC circuit results, the theoretical model predicts that the voltage and current in an RC circuit decays exponentially with a time constant equal to RC. Based on the circuit values, the expected time constant was approximately 10 seconds, but our measured charging time of 10.73 seconds agrees closely with this prediction. However, the longer discharging time of 14.07 seconds likely results from non-ideal resistance changes in the light bulb and internal circuit effects. Here are some results just showing the time constant model, whereas you can see when that graph begins to level off, that is one time constant. So the first question we want to ask ourselves to conclude this lab is, what if we had more than one light bulb or resistor that was included in the RC circuit? Well, if those bulbs were in series, that means that the total resistance is the sum of the resistance from each bulb. This is going to increase the resistance. So current decreases, capacitors charge and discharge more slowly, time constant increases, and the bulbs dim more slowly. This results in a graph where exponential decay is more gradual. However, if those bulbs are in parallel, the total resistance is going to be the inverse sum, so it's going to be a decrease. So everything in the series part is then reversed, so that exponential decay is going to occur much faster. So the last question is, what does it physically mean for energy to be transferred from the capacitor to the bulb? Well, when a capacitor is charged, there is charge separation in the plates and electric field exists. When that capacitor is discharged, the charge separation decreases, the electric field weakens, and the energy that was contained in that electrical field is transferred to the rest of the circuit.